Hello everyone. Today's lecture is going to talk about a very important class of machine learning methods for materials and in particular molecular data based on kernel machine learning models. So given the fact that kernel regression techniques are important enough in their own right, and the fact that there's been a real steady stream of research on how advantages of kernel learning can be used for machine learning, we decided that it's worth an entire lecture to explain all the intricacies of these kinds of methods. So before we get too deep into this particular subject, we'll start off with some foundational machine learning. So kernel methods are based around the concept, which we're going to refer to as the kernel trick, where I can transform my data from a low to a higher dimensional space using a pairwise similarity or kernel function. And this kernel trick makes it possible to train easier or simpler machine learning models. With a good example of this being the cartoon we have on the right, where I'm trying to build a machine learning model that separates these two classes of data, and the only data point I have about them is a single variable, which we're calling x. Now, if I try to train a machine learning model on this original low-dimensional space of x, it would be very complicated. But if I apply a kernel where I take and compute the similarity between different points, let's say I'm going to have one that's roughly based on the distance from that middle point, I can change the feature space. In fact, I'm making it higher dimensional. Applying this kernel function gives me 5 features instead of 1. But this does create one feature, feature 2, that allows this problem to become linearly separable. I can have a single decision surface that separates the two kinds of data. So this overall concept of being able to come up with these kernels that turn an otherwise complicated machine learning model or machine learning problem into something very simple has a lot of impacts on chemistry. Now, before we get into this full lecture explaining what those are, we're going to just name down a few terms. This pairwise similarity metric, we're going to call the kernel function. And if I take this kernel function and I apply it to all pairs of data within my data set, I create a kernel matrix. And many of the machine learning techniques, such as kernel ridge regression, rely on performing operations on this kernel matrix, such as a ridge regression where I have, in effect, a linear regression model where I sum up the contributions of the kernel functions between a point I'm trying to evaluate and all of those points in another set, which can be represented both as a matrix operation or as this summation function here. The two are equivalent. Now these kernel functions, outside of having this conceptually kind of beautiful trick that lets us train good machine learning models, they also have a number of very beneficial machine learning properties. They're an instance-based technique, which means that the number of parameters in the model increases with the number of data points. In fact, kernel ridge regression, you get 1 parameter per data point. So this gives you models that kind of naturally become more accurate the more data you train them. And you can often find this linear relationship between the log of your training set size and the log of the test error, which is excellent. Additionally, there's a similar class of techniques called Gaussian process regression that uses kernel functions to build some very well understood classes of probabilistic models that allow you to get some estimates on the uncertainty of each of your predictions. And GPR is Gaussian process regression. There's also a lot of ways you can bake in different kinds of physics into a machine learning model based on kernels. For example, I can use a sinusoid function as one of my kernels, combine it with a nonlinear function like these Gaussians, and get a machine learning model that captures both, say, seasonal variability within atmospheric carbon dioxide levels and its nonlinear change over time. So I can make a very simple function that actually captures a lot of the underlying physics. And there's also wonderful classes of techniques like co-kriging, which allows you to train a machine learning model on two different fidelities of data. Say for a single point, I can get a quick estimate or a very expensive one for its properties. Co-kriging, which is a multi-resolution or multi-fidelity method, allows me to train a machine learning model on both kinds of data in a way that gives me a model that would be better than if I trained on the high or the low fidelity data individually. And this technique is built upon these concepts of kernels. So in terms of taking this kind of very mathematical type of machine learning and applying it to materials, there are actually a lot of different ways you can think about developing it. And this is well reflected in the half dozen or more methods for kernel-based molecular machine learning that have been invented in only the past decade. And if you really want to get a history of them, you can follow work by Anatol von Leeuwenfeld's group, where they have actually contributed many of these different kernel methods on the plot here. How all these different methods vary are by changing the different kinds of physics that we put into the machine learning kernel. Just like in that example of atmospheric carbon dioxide levels, where we know there's seasonal variations and I can use a sinusoid in that kernel function. There are many different other kinds of ways we can introduce physics, and we'll talk about a few of them here. For example, I may want to be able to interpolate between changing a type of an atom, say a material that contains carbon in a similar environment is closer to one that contains nitrogen because it's nearby on the periodic table compared to one that contains iron. That's the kind of similarity you can put into your kernel function that allows you to do machine learning better. There are also ways you can design these kernels to be sensitive to small changes in the environment. Say if I take a bond in a material and I slightly stretch it. Additionally, I can make them insensitive or invariant to other kinds of changes in a molecule, like taking its coordinates and rotating them about a point, or translating them in space, or changing the ways that I order atoms, and make my machine learning model actually resistant or have no changes regardless of how I apply these changes to a material, which is a good thing with things like energy. The energy of a water molecule doesn't change if I have it right side up or upside down. And one of the examples that illustrates a lot of these points is one of the early kernel-based methods in machine learning known as the Coulomb matrix. So the Coulomb matrix is defined by a simple formula where my diagonal components of this matrix are encodings of the atomic number of each of my atoms. Here in this notation, I and J are the index of atoms within a molecule. And as I mentioned, these on-axis points encode information about a molecule, or about an atom. The off-axis, or the off-diagonal terms, encode, say, the distance between different atoms in a molecule multiplied by their charges. And in this way, I have a representation that captures the changes in chemistry through these Z and changes in coordinates through these R's. And the cool thing about this is the way I treat the coordinates is I take pairwise distances, which these are insensitive to whether I rotate a molecule. If I flip it upside down, the distance between two atoms are always the same. The way that I turn this into a kernel function solves another problem. I take this kernel matrix and I compute eigenvalues, which produce a string of numbers that are invariant to if I, say, renumber the atoms in a molecule. And I can take the differences and I can sum them, or I can sum of the squares of the distances, and that gives me a good kernel matrix describing two different two different molecules. So that is, to be in short, I take my matrix for each of the molecules, I compute the eigenvalues, and then I subtract the eigenvalues between two different molecules to get my kernel function. And this kernel function has some good properties. I can see that changes between chemistry are often reflected in large distances. If I change far on the periodic table, like nitrogen to sulfur, compared to having, say, carbon change to oxygen between these two kinds of molecules here. And additionally, I can find through statistics of molecules that I find that, say, the farther in distance I go between two different molecules, generally the larger difference between their energies, and you can see that reflected in this large plot here. Again, larger distance between molecules, larger distance in energy. So this gives me a pretty good function. I've got a distance metric that has some physical meaning, and it creates my ability to train good machine learning models. And this is from around 2012, and there have been rapid advancements since then. One of the more recent ones is work by Felix Faber and Anatole von Lilienfeld called the FCHL representation, where F is Faber, L is Lilienfeld, and these two are the other co-authors. The way that FCHL works is very similar to the Coulomb matrix. I take each of my atoms and I describe them using a representation that describes them as Gaussian functions, where that function takes in the position on the periodic table as an input and bond distances and angles between the atoms, giving me these Gaussians that look like this. And then I can capture the similarity between atoms by taking the overlap integral between those different kinds of Gaussian functions. So as an example, one is just based on the one-body term, or just the atom itself and not any of its neighbors. And I can describe it via this Gaussian, where I have changes in position or changes in value the farther I deviate from the period or the group of that atom. Now, if I want to calculate its similarity to another atom's environment, I can take this overlap integral, where you note I'm integrating over these variables x and y, which I just told you have to deal with whether this point is close to or far from the period. And because these are Gaussian functions, this integral is analytically solvable, and I get a nice function where I see if an atom has a period, a very different period, or a very different group compared to another. I get larger or smaller values of this overlap integral. So that has a good method for a kernel function. Now this here I've mentioned describes similarities between atoms in a way that captures here the differences in chemistry, and also if I go to the many-body analogs, like what are shown in this cartoon here, I can capture bond distances and angles as well. I need to turn that into a way of defining the similarity between not just single atoms, but entire molecules. And for this, I use a technique, or FCHL used a technique known as scalable kernels. So here, I try to take my atomic similarity functions and build them up in a way that encodes an atomic similarity to molecular property relationship. And for the case of energy, I know that I can decompose the energy of a molecule into contributions from individual atoms very easily. It's a very good approximation. So if I find this so-called scalable kernel, where I define my comparison between two different molecules, x and y, as a sum over the comparisons between their atoms, this possesses that similar property where my energy tends to scale linearly with my atomic size, and that is captured right in my kernel. And in that way, I not only create my ability to define similarities between molecules, which I can use with techniques like kernel ridge regression that we mentioned earlier, but it does so in a way that captures my understanding of the physics of the problem. We've got a whole machine learning or Jupyter notebook that illustrates this entire concept, noting that the ideas behind FCHL and scalable kernels are quite complicated. we break them out down to each individual step in one of the notebooks available with this lesson. Now that I've shown you the kind of good sides and practical ways that kernel ridge regression is used, one of the features of it that you really need to know about before being able to practice kernel learning well is its downside. And that has to do with how well kernel methods scale with the amount of training data that you have available. Now, if you remember from the introduction of the kernel matrix, that kernel matrix is composed of every pairwise comparison between entries in the training set. So that means that in order to compute the entire matrix, I have a computational cost that scales with the square of the number of training entries. And you can actually see that. This here is the timings that I've measured for training an FCHL model. And you can see that as I start to get to larger training set sizes, my time for training scales with about the square of the number of training points. And there's even another computational cost to this that it isn't yet important enough at these small training set sizes, but as you go even farther, the cost to solve a matrix inversion that's present in kernel ridge regression scales with the cube of the number of training points. That could indeed become a problem. Additionally, when I'm making a new inference from the machine learning model, I have to make a comparison between my new point and each of the training points, which means that the time to evaluate scales linearly. So the ways of getting around this often are defined by, say, picking special points within your space of molecules, as shown in this paper by Browning and others, where if you pick only these special points rather than every single point in your training set, which are shown by the kind of the dark variations of gray in the background, you can have a machine learning model that performs just as well, but avoids these kind of large scaling costs. So really, if I were to reframe this from being a problem with kernel methods to an opportunity, is that it allows you to dial in your performance versus accuracy. I can pick just enough training points to give me the computational costs that I want, and I can get a maximized accuracy in my machine learning model. Another problem with kernel ridge regression is that you have to be very sensitive about how you choose the hyperparameters for a model. And this is described well by a review paper from Matthias Rupp, where he shows a cartoon example of what happens when you try to fit this parabolic curve with a kernel ridge regression model. And you can see that if I pick this kernel width too small, I get a model that has these sharp peaks in it, so it fits my training data perfectly. You can see that at these 4 points that he gave us training data, I fit the model exactly, but in the opposite regions it does much worse. Rather, if I pick a reasonable value, I can fit this nonlinear curve very well, and if I pick too large of a smoothing value, I don't fit my training data well enough. So that's very important. And so that means also that you have to find a good value of, say, the sigma parameter in particular before you can actually measure how well your kernel-based machine learning model is doing. If you guess this wrong, you can get a very bad picture or a very wrong picture about how accurate the model could be. Secondly, these hyperparameters also their optimal value tends to change dramatically with your training set size. So this isn't just a cost you have to pay once, but you have to pay many times if you were to, say, train your machine learning model at different times. Excellent. So moving on from here, some of the exposure you'll get through the practical part of this lecture, I'll be showing you some of the many machine learning codes that are being available to help you build machine learning models. In particular, they're the dscribe and QML packages that allow you to compute many of those different machine learning methods that we described earlier. Indeed, the work from FCHL, which is Faber, Christensen, Hung, and Lelandfeld, are also the people who developed the machine learning model, or the machine learning code available to help you use it. So to wrap it up today, the things that I want you to remember about kernel methods are that they're based around this idea that I can make machine learning models easier to train if I apply some kernel that makes my initial training data higher dimensional. There are many of these such kernels made for molecules, and if you can get around the learning curve to being able to use them, they can be very powerful tools. Because indeed, for many of these challenge problems available in materials science, kernel methods are often the best performing, and it's still a very active area of research. So it's my expectation that kernel methods are not going to go away anytime soon, and indeed may be a go-to machine learning approach for years or decades further. So that wraps up our lecture for today. I'll be also making some notebooks available to you that give you the hands-on exposure to these techniques, and they'll be available on our course GitHub page.